Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's get started on our set of questions for today's session. Okay, so question 1 asks how many valence electrons do chlorine, bromine, and iodine have? Okay, so chlorine, bromine, and iodine. So let's look up these elements on the periodic table. Okay, so if we look at a periodic table, we'll see that all three of these elements, chlorine, bromine, and iodine, they're in the same group. So they're all in group 7A. So all of the elements in group 7A have 7 valence electrons. Excuse me. So for example, if we were to draw chlorine, it has the atomic number 19, I believe. That means if it was a neutral chlorine atom, then it would also have 19 electrons. So if we were to sketch out all of the electrons in these shells, we would have 2 in the inner shell, and then 8 in the next shell. So now we have 10 out of the 19. And then, actually, I think its atomic number is 17. Yeah, so it's 17. That makes more sense. I think its atomic mass is 19. Okay, so now I have 10 out of the 17. So I need to draw in 7 more. And we have 7 valence electrons in this shell. And if we were to compare it to fluorine, fluorine has an atomic number of 9. So similarly, we can sketch out what its atom may look like. Okay, so here's 7 valence electrons as well, except its atomic radius is much smaller than compared to chlorine's. Okay, so this is how all 3 of them all have 7 valence electrons. And the junior tutor said that valence electrons are the electrons found on the outermost shell of an element or ion. Also corresponds to the group number of the element on the periodic table. Therefore, for the following elements, fluorine, bromine, and iodine all have 7 valence electrons. So this solution is correct. Okay, so question number 2 is to draw the Lewis structure for sulfur trioxide molecule. Be sure to include all resonance structures that satisfy the octet rule. Okay, so sulfur trioxide, if we were to draw its Lewis structure, we first need to find out the total number of valence electrons for this molecule. Okay, so sulfur has 6 valence electrons, and oxygen also has 6. But since there are 3 oxygen atoms, we multiply this by 3. So in total, this gives us 24 valence electrons. Okay, so now let's try to draw out a skeletal structure for this molecule. Sulfur will be our central atom since it is less electronegative than oxygen. And then we can draw 3 bonds to our oxygens, and we'll see what happens if we draw in all of our lone pairs. Okay, so if I count out how many electrons I have in this structure, where each bond contains 2 bonding electrons, then you'll see that I already have my 24. But my sulfur doesn't have a full octet yet, so I'm just going to bring a pair of electrons down to form a double bond, like so, and we get the following structure. But we'll also take into account that my oxygens will have a negative charge if I were to calculate the formal charge of these atoms. So for both of these, I'm just going to bring these electrons down to again form double bonds. And a pair of electrons will be gone to give us the following structure. Okay, so now if I double check and if I were to calculate the formal charge of all of my atoms, I can use the equation for formal charge, which is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So first let's do it for all of the oxygens. Oxygen has 6 valence electrons, and there are 4 non-bonding electrons on each oxygen atom. And since each of them have a double bond, they contain 4 bonding electrons in total, which we divide by 2 to get a formal charge of 0. So now let's do the same thing for our sulfur. Sulfur has 6 valence electrons, and there are 0 non-bonding electrons, which are 0 lone pairs. And there are 6 bonds to sulfur, so we have 12 bonding electrons divided by 2. So this also shows sulfur having a 0 formal charge. So since all of the atoms have a formal charge of 0, then this is the preferred Lewis structure for SO3. Okay, so the junior tutor said that the Lewis structure for sulfur trioxide is the following. As observed, the Lewis structure follows the expanded octet rule, where the total valence electrons of the compound is 24. Since SO3 follows the expanded octet rule, in order to draw the resonance structures that follow the octet rule, we would use SO3 2-. Okay, so they showed how you could also have SO3 2-. If you were to gain an extra 2 electrons, then we can draw resonance structures that follow the octet rule. So this solution is correct. Okay, so question number 3. What is the Lewis structure of ethyl alcohol? C2H5OH. So when drawing the Lewis structure, we first need to calculate the total number of valence electrons for this molecule. So carbon has 4 valence electrons, and we have 2 atoms of carbon, so we multiply this by 2. Hydrogen has 1 valence electron, and in total for this molecule we have 6 hydrogens. And then lastly, oxygen has 6 valence electrons. So adding these values up, we have a total of 20 electrons for this Lewis structure. So now if we try to draw a skeletal structure for ethyl alcohol, we can show that one carbon can be bonded to another carbon, and we can draw 3 hydrogens out of the 5 or out of the 6 on the first one, and show how the oxygen is bonded to the second one. And now we just need to fill in all of the remaining hydrogens like so. And if we count out how many electrons I've drawn so far, recalling that each bond contains 2 bonding electrons, we have 16 out of the 20 electrons drawn in this structure. So for the remaining 4 electrons, I can put them as lone pairs on my oxygens. So now I have the correct Lewis structure for ethyl alcohol. And notice that when we named ethyl alcohol, since we have a 2-carbon chain, we would use the prefix ethyl, and the alcohol group can only be on carbon 1, like even if it was on the second carbon, it would also be considered carbon 1. So then we just put ethyl alcohol, or we can also call it ethanol, which is the same name. Okay, so the junior tutor said that the Lewis structure of a molecule is the easiest way to represent a molecule with different electron pairs. Electron pairs may be in the form of bonds or lone pairs, and lone pairs are pairs of valence electrons that are unshared and usually represented as pairs of dots surrounding an element. On the other hand, bonds are represented as a line connecting 2 atoms. Properly draw the Lewis structure of a compound, we follow the steps below. Step 1, find the total number of valence electrons. So this is done by adding all the valence electrons from the atoms. And step 2, we find the number of electrons needed to make the atoms follow the octet rule. Elements up to period 4 on the periodic table need to follow this rule except for hydrogen. In addition, elements from period 5 can have an expanded octet. Step 3 is to determine the number of bonds in the molecule. This can be done using the formula step 2 minus step 1 divided by 2. Then we choose the central atom. So usually it's the least electronegative or the one with the highest valence electrons. So in our case, carbon isn't the least electronegative, it's actually hydrogen. So the fact that it can form multiple bonds is the reason why we made carbon our central atom. Step 5 is to draw a skeletal structure. And step 6 is to place electrons around the outside atoms. And step 7 is to place any remaining electrons around the central atom. Okay, so they got the correct Lewis structure. So this solution is correct. Okay, so question number 4 is to draw the structure of guanine. So guanine is one of the main nitrogenous bases. And it can be found in DNA. It's also a purine ring, meaning it is formed with 2 rings. Okay, so let's draw out the structure. In the first cyclic ring, we have a 5-membered aromatic, just involving 2 nitrogens. And then in the second ring, we have a 6-membered ring with a double bonded oxygen and another amine group on the side. So this is the structure of guanine. And if we look at the junior tutor's answers, they said that guanine is among the 4 main nitrogenous bases, specifically a purine derivative that can be found in DNA and RNA. Purines generally have 2 rings in their structure, and the chemical formula for guanine is C5H5N5O. Yep. The structure of guanine is shown below, which aside from the 2 rings is attached to an amino group and an H and has a double bond with oxygen. Okay, so this solution is correct. Okay, so question number 5. Would you expect the molecule H3O plus to be polar? A lot or a little, and why? Okay, so first let's draw the Lewis structure for H3O plus, which is also known as the hydronium ion. So we first need to find out the total number of valence electrons for this ion. Hydrogen has 1 valence electron, and we have 3 hydrogens, so we multiply this by 3. Oxygen has 6, and since the overall charge of this ion is +1, we need to subtract 1 electron from our total electron count. Okay, so if we add these values up, we get a total of 8 electrons in this Lewis structure. So now let's draw oxygen as our central atom. And we can draw 3 bonds to the hydrogens. And if we count out how many electrons I've drawn so far, then where we recall that each bond contains 2 bonding electrons, I only have 6 out of the 8 that I need. So for the remaining 2 electrons, I will place them on my central atom, which is the oxygen. So now we have a valid Lewis structure, but we also need to take into account the formal charges of these atoms. So the equation for formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So let's calculate the formal charge of one of the hydrogen atoms. Hydrogen has one valence electron, and since there are no lone pairs on hydrogen, there are 0 non-bonding electrons, and because there's a single bond containing 2 bonding electrons, we have 2 divided by 2. So hydrogen has a formal charge of 0. And we can do the same thing for oxygen. Oxygen has 6 valence electrons. There are 2 non-bonding electrons in the form of the lone pairs. And finally, there are 6 bonds, or 3 bonds to hydrogen, each bond containing 2 bonding electrons. So in total, we have 6 bonding electrons divided by 2. So 6 minus 2 minus 5 is positive 1. So now we know that our oxygen will be the one to carry the formal positive charge, positive 1. Okay, so the second part of the question asks if we expect this molecule to be polar. A lot or a little, and why? So to find out whether or not a molecule is polar or nonpolar, we need to find out the difference in electronegativities between the atoms involved. So this will tell us if the bonds are polar. So let's calculate the electronegativity difference between oxygen and hydrogen. So I can use a periodic table that shows all the different electronegativity values. Okay, so here's one. And if we find the electronegativity value of oxygen, it's 3.5. And for hydrogen, it's only 2.1. So the difference between the two is 1.4. So therefore, the oxygen-hydrogen bond is polar. And this is since our electronegativity difference is greater than 0.4, but it's less than 1.69. So therefore, we have a polar bond. So if we were to draw little dipole moments, they would be pointed towards our more electronegative oxygen. And also, we have a lone pair on our structure as well. So let's look up what this structure is actually called, like its molecular shape. And to do that, we would need to analyze our oxygen, and we'll see that it contains 1 lone pair and 3 bonded atoms. So using a Vesper theory table, when we have 1 lone pair and 3 bonded atoms, we have a trigonal pyramid molecular shape. And notice that the dipole moments don't cancel each other out. So therefore, H3O plus is also polar. We also have a net zero dipole moment, a net non-zero dipole moment. And even the fact that we have a charge makes it polar as well. So I'll add that up here. Positive charge also tells us we have a polar molecule. So therefore, the answer is that we have a very polar hydronium ion. And the junior tutor said that we can look at the Lewis structure of hydronium ion to check whether it's polar or nonpolar. The hydronium ion has an oxygen, which will be the central atom of the Lewis structure, with the 3 hydrogen atoms bonded to it. It has 8 total valence electrons, and it can be written like so. We can see that there is a lone pair of electrons in the oxygen. This means that there is a repulsion present in the molecule, making the dipole moment of the molecule non-zero. Hence, it's polar. Molecule has a strong polar properties since the molecule has a hydrogen bonded to an oxygen that can be resulted in hydrogen bonding. Hydrogen bonding has strong polar properties because of the considerable electronegativity difference between the oxygen and the hydrogen atom. Okay, so this solution is correct. Okay, so question number 6. What is the name of the compound Se4S4? Okay, so if we were to analyze the type of compound we have, you'll notice that we have 2 nonmetals, selenium and sulfur. So therefore, we have a binary covalent compound. So the reason why we want to find out the type of compound we have is because depending on whether or not it's a metal, an ionic compound or covalent compound, they're going to follow a different set of rules in naming them. So the first step in naming binary covalent compounds is to write your first element and if there is more than one, we include a prefix. Okay, so I can summarize all the different prefixes just over here on the right. When we have 1 atom, we use the prefix of mono. When we have 2, we use di. 3 is tri. 4 is tetra. 5 is penta. 6 is hexa. 7 hepta. 8 is octa. 9 is nona. And 10 is deca. Okay, so these are all the different prefixes that will be helpful in naming these compounds. So now step 2 is to write our second element. And we would always use a prefix, even if there's only one, to show how many atoms we have. And also when writing the second element, we would use the ending "-ide" when writing out the name. So now for our example, we have selenium and sulfur. So if I were to follow these rules, first I would write my first element, which is selenium, and since there's more than one selenium atom, I would use the prefix. So I would write tetra selenium. And then for my second step, I need to write the second element and use the prefix of tetra again. So tetra. And then from here, I would write out sulfur, except instead of continuing writing sulfur, I would end it in "-ide". Okay, so the name of this compound is tetraselenium tetrasulfide. And the junior tutor said that in naming binary compounds, the most metallic element comes first with its elemental name, and the nonmetal would be the second element with its elemental name ending in "-ide". Prefix is added to the first and second element, indicating its number of atoms, but if the first element exists only as one atom, prefix mono is not added and its elemental name is retained. Therefore, the name of Se4S4 is tetraselenium tetrasulfide. Okay, so this solution is correct. Okay, so question number 7 is to draw the Lewis structure for CH3NO2 and include all lone pairs and electrons. Okay, so when writing out the Lewis structure, we first need to calculate the total number of valence electrons. So carbon has 4 valence electrons. Hydrogen has 1. And since we have 3 hydrogen atoms, we multiply this by 3. Nitrogen has 5 valence electrons. And oxygen has 6. And since there are 2 oxygen atoms, we'd multiply this by 2. So this gives us a total of 24 valence electrons. Okay, so now let's try to draw out a Lewis structure for this compound. We would have carbon bonded with 3 hydrogens, and then also bonded to the nitrogen, like so. So let's count out how many electrons I have in this structure. We would have 10 out of the 24 electrons. So let's see what happens if I draw in all of the lone pairs on my oxygens. So this gives us 22 out of the 24. So I'm going to also show that since nitrogen doesn't have a full octet yet, I'll bring down a pair of electrons to form a double bond. And now we have (24) electrons in this structure. Okay, so we're almost done. We just need to calculate the formal charge of all of our ions. And one of the rules of thumb is to have the most electronegative atom carry a negative charge if there is one. Okay, so let's calculate the formal charges. So the equation for formal charge is the number of valence electrons minus the number of non-bonding electrons minus the number of bonding electrons divided by 2. So let's calculate the formal charge of one of the hydrogens. Hydrogen has 1 valence electron, 0 non-bonding electrons, and all of the hydrogens just have a single bond. So each bond contains 2 bonding electrons that we divide by 2, and we get a formal charge of 0. So for the carbon has 4 valence electrons, 0 non-bonding electrons, and there are 4 bonds to the carbon, so we have 8 bonding electrons divided by 2. So we also have a formal charge of 0. So now let's calculate the formal charge of nitrogen. Nitrogen has 5 valence electrons, and there are no lone pairs on the nitrogen, so we have 0 non-bonding electrons. And there are 4 bonds to our nitrogen, so we have 8 bonding electrons divided by 2. So the nitrogen will carry a positive 1 charge. So we can show that on our structure. A bit too close. Like so. And now we can continue on to calculate the formal charges of both of our oxygens. So for the double bonded oxygen, there are 6 valence electrons, 4 non-bonding electrons, and there are 2 bonds to the oxygen, so we have 8 bonding electrons divided by 2. 4 bonding electrons divided by 2. So we'd have a formal charge of 0. And lastly, we have our single bonded oxygen. There are 6 valence electrons, 6 non-bonding electrons, and just a single bond, so we have 2 bonding electrons divided by 2. So our oxygen will carry the negative charge, which is preferred since oxygen is the most electronegative in this atom. So then when we are to calculate the total charge of the compound, it's just going to be the sum of all of the formal charges. So we have -1 from the oxygen, and we have +1 from the nitrogen, making an overall neutral compound. Okay, so this is the correct Lewis structure for CH3NO2. And the junior tutor said that for step 1, arrange the symbols in this way that the electronegative element is in the center and other elements surrounding it. Step 2, give each of the elements their appropriate number of electrons, dots. Hydrogen has 1, carbon has 4, nitrogen has 5, oxygen has 6. And they did the math and found 24 valence electrons. Step 3 was to draw the Lewis structure. Okay, so they showed the positive charge on the nitrogen and the negative charge on the single bonded oxygen. So this solution is correct. Okay, so question number 8. Aluminum carbonate, Al2CO33, is used in fire extinguishers since it decomposes when mixed with water and releases carbon dioxide, which prevents combustion. That's interesting. So A, what is the percentage composition of aluminum carbonate? Okay, so to answer this question, we would need all of the individual atomic masses of the atoms involved in aluminum carbonate. So we can look their values up on the periodic table. So I don't know aluminums off the top of my head. So if we looked up the molar mass of aluminum, it's around 26.98 grams per mole. And we also need the molar mass of carbon and oxygen. So the molar mass of carbon is 12.01 grams per mole. And the molar mass of oxygen is around 16 grams per mole. And we also need the total molar mass of aluminum carbonate. So let's write that down on the right side here. So when finding the molar mass of a compound, we need to take into account how many of each atom there is in the compound. So we have 2 atoms of aluminum. So it's going to be 2 times the molar mass of aluminum plus 3 times the molar mass of carbon plus 3 times 3 for the oxygens. So we have 9 times the molar mass of oxygen. So now we just need to plug in all the values that we found from the periodic table. Aluminum's was 26.98. Carbon's is 12.01. And oxygen is 16. So the total molar mass of the entire compound is 233.99 grams per mole. Okay, so now we have all the individual atomic masses for our elements, and we also have the total molar mass of aluminum carbonate. So now when finding the percent composition, we need to take into account all of the elements and also how much of each element there is in aluminum carbonate. So for example, let's calculate the percent composition of aluminum. So we have 2 atoms of aluminum in aluminum carbonate, and we also know the molar mass of aluminum is 26.98 grams per mole. So now we just divide this by the total molar mass, which we found to be was 23.99. So we get a percent composition of around 23.1%. And this is for aluminum. So now let's look up the percentage of carbon. So there are 3 atoms of carbon. Carbon's molar mass is 12.01 grams per mole. And again, the total molar mass is 233.99. Oh, forgot to add that we need to multiply by 100. Obviously, get the percentage. So all of this multiplied by 100 gives us a percent composition of around 15.4% of carbon. And now let's calculate the percentage of oxygen. So there are 9 oxygen atoms, And the molar mass of oxygen is 16. And then we divide by the total molar mass, which is 233.99. And let's not forget to multiply by 100% to convert this decimal into a percentage. And we get 61.5% of this aluminum carbonate is oxygen. So now we can double check to see if all of these percentages add up. So aluminum carbonate is 23.1% aluminum, 15.4% carbon, and 61.5% oxygen. So let's double check to see if we did it correctly by adding up all these percentages. And we get 100%, which is good. Okay, so now let's see what the junior tutor said. The percent composition is the percentage of each element that is in the compound, and to find the percent composition, we first have to find the molecular weight of the compound and then relate the molar mass of an element to the molecular weight. The molecular weight of a compound is equal to the sum of the molecular weights of the atoms that are in the compound. So for aluminum carbonate, we have 2 times the molar mass of aluminum plus 3 times the molar mass of carbon plus 9 times the molar mass of oxygen to give 233.99 grams per mole. So they have the percent composition of aluminum equal to around 23, carbons is around 15, and oxygens is around 62. Okay, so this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a thumbs up or a comment and share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon.